This is our first lesson in Unit 4 or 5, where we are starting to talk about probability itself. So what we're going to cover today is sample space and events, and mainly this is just going to be terminology. We want to take our knowledge of sets that we gained in the previous units, and we want to be able to organize and communicate the results of experiments. What is an experiment? Well, we'll talk about that a little bit. And then we want to be able to, for a given experiment, list the sample space, event spaces, and cardinality of events and compound events. And we want to understand what all of these terms mean. Where we are going is we are going to try to calculate the probability of events. And one of the things that we need to calculate if we are going to talk about the probability of an event is the number of ways that an event can occur. So this is where all of the stuff we did on permutations and combinations and organized counting is going to get applied to calculate probabilities. But first, let's just figure out what all of these terms mean about sample spaces and event spaces. So what do we mean by an experiment? Well, the definition I came up with here is anything that happens that has specific results, and we kind of record what these results are. This is a vague definition, but we want some sort of an activity where there are certain discrete, identifiable things that can happen as a result. And we take note of these results. So a good example that we're going to work with here is something like rolling a six-sided die. Okay, we roll the die as our experiment, and there are very specific results that can occur. We can get a 1, we can get a 2, we can get a 3, and so on and so on. When we use the word outcome, what we're talking about is one of these results that can happen in an experiment. Okay? So whatever is on the top of the die after we roll it is our outcome. We are going to talk a lot about the sample space. Okay? And the sample space is the set of all of the possible outcomes that can occur for our experiment. So we usually denote the sample space with the capital letter S. It's a set. So for our example here, what is the set of all outcomes that are in our sample space? Well, we can roll a 1, a 2, a 3, a 4, a 5, or a 6. So the outcomes are 1, 2, 3, 4, 5, and 6. So we've listed all of the possible outcomes in our set S that represents our sample space. You will often see this notation as well. Small letter n with a letter identifying a set in brackets there. When we see that, we are interested in the number of elements that are in our set. So how many outcomes are there in our sample space? There are a grand total of 6. Now what we will be concerned with is what we call the event space, or to shorten it up a little bit, an event. So an event is just some subset of the sample space that we have a particular interest in, or that we are trying to investigate somehow. So we could say something like, for our example here, we could define an event or an event space E1. Okay, we just use E for event. We'll call it 1 to distinguish it from all the others. Let's say E1 is the event where we roll a 1. E1, this event space, is a set. Okay? So we can write it as a set like this. Now, how many outcomes are there in this set? There's just 1, okay? Because it's just the set, the outcome where we roll a 1. So E1 here is a subset of our sample space. Okay? 1 is contained in our sample space. It's also in our set E1 here. So what we're saying here is that there's 1 outcome in this event that we've listed, E1. So we could have another event in our same sample space. So let's say we'll have one called E2 here. Let's say E2 is the event where we roll less than a 4. Let's say less than 4. So what outcomes do we have in the event space E2? Well, 1 is less than 4, 2, 3, 4. Those are the possible outcomes, 1, 2, 3, and 4, that correspond to this event that we are interested in. Okay, so we have, should I have 4 in there? Ryan's shaking his head. No, I shouldn't, because I said it should be less than 4, so I should take out that 4. So we have 3 outcomes in this event space that corresponds to the event we roll less than a 4. I don't know, we could come up with something else. E3 is the event where we roll a prime number. So E3 is equal to, let's see, what are our prime numbers here? 1 is a prime number, 2 is a prime number, 3 is, 4 isn't, but 5 is. Prime numbers are divisible only by 1 in themselves. So we have 4 possible outcomes in our event E3. Now, of course, there are a lot of other prime numbers, but none of those other prime numbers are contained within our sample space, so they aren't possible outcomes for our event. Okay. So this is what we mean when we talk about events. Now, we will also talk about the cardinality of an event. And this just means the number of elements that are contained in the event subset. So for our 3 events that we have, we can talk about the number of elements that are in each of these 3 events. So the number of elements in event 1, where we were rolling a 1, it's just 1. Number of elements in 2 was 3. And then the number of elements, the number of outcomes in our event 3, where we're rolling a prime number, was 4. So when we say elements here, these are elements of the set or outcomes for our experiment. So this is all pretty straightforward. A lot of the time we are going to be considering what we call a compound experiment, which is where we take 2 experiments or multiple trials of the same experiment and we consider them together. So something like if we roll 2, and I'll use the written word 2 here, 2 6-sided dice. Okay. And we consider what we have on both of the dice. Because we're considering these both at the same time, this is a compound experiment. So we could consider the sample spaces for our two experiments separately at first. So we could say when we roll die number 1, we have 1 sample space. What are the possible outcomes? Well, 2, 3, 4, 5, and 6. For die number 2, it will have, this other experiment will have its own sample space with the same possible outcomes. 4, 5, and 6. If we're considering these 2 things together as 1 experiment, our overall sample space, just S, our overall experiment, is going to be the combination of our 2 individual sample spaces. So how do we list this combination, this sample space for our compound experiment. Well, we can list, kind of like as ordered pairs, the possibilities on die 1 and die 2. We could get a 1 on the first one and a 1 on the second one. So we put 1 comma 1 in round brackets there. We could have 2 and 1. We could have 3 and 1. Okay. So we're listing the possibilities of things that'll turn up on both the first die and the second die. And so on and so on and so on. And then we could have 1 comma 2, 2 comma 2, so on and so on and so on. Okay? So you sort of see the pattern there. We're not going to list out everything here that we have in our sample space. Now, what if we are just interested in the cardinality of that sample space? In other words, the number of elements in our sample space S. Well, we're going to take the number of elements in our first sample space for die 1, and multiply it by the number of elements in the sample space for die 2. Okay. How do we know that we're supposed to do this? Think back to Unit 1, where we talked about the fundamental counting principle. Principle. Okay. It told us that if we had a two-stage process, we would multiply the number of possibilities at each stage. So the number of elements, or the cardinality of our combined sample space, is 6 times 6, or 36. So let's just consider 2 possible questions that could arise if we consider this compound experiment where we're rolling 2 6-sided dice. Okay? So our experiment's up at the top. How many ways can the numbers showing add up to 5? Okay? So we want to list the event space first, and then we want the cardinality of that event space, okay? Or the number of ways. So let's define our event first. E1 is the event where numbers add to 5. Well, what possibilities are there in our event space here? We could have a 1 on the first die and a 4 on the second. We could have a 2 on the first one and a 3 on the second. We could have a 3 on the first one and a 2 on the second. And then we could have a 4 on the first one and a 1 on the second. So I'll just put in the little note here that this is the first die, and that number represents the second die. So there's our event space. How many elements do we have in our event space? We have 4. So our next one here. The player wins. Let's assume we're playing like some little game here. And the player wins something if they roll a sum greater than 9 or doubles. How many ways can they win this little game? So we have 2 possible events that we want to consider here. The event that they roll a sum greater than 9, or the event that they roll doubles. So let's define these 2 event spaces. Okay? We'll have a big event space, E. Let E be the event where the player wins. And we'll define E1 as the event, well, and that's not how you spell where, it's got an E on the end, where, let's say they roll greater than 9. The player rolls greater than 9. And we'll have another event space, E2, which is the event where the player rolls doubles. Player rolls doubles. So let's list out our event spaces for E1 and E2, and then consider the combined event space, capital E. So E1, rolls greater than 9. How many possible ways could they roll something greater than 9? Well, let's see. On the first die, they could get a 6. On the second one, they could get a 4. That would add up to 10. They could get a 6 and a 5. That would add up to 11. They could get a 6 and a 6. That would add up to 12. If they didn't get a 6 on the first die, they could get a 5 on the first die, and then get a, well, if they got a 4, it wouldn't work, but they could get a 5 on the second die, because that would give them 10. Or they could roll a 5 and a 6, which would give them 11. Is there any other way they can get something that is greater than 9 here? Well, they could roll a 4 on the first one, and a 6 on the second one. So I think those are all the possibilities for rolling greater than 9. So how many things do we have in this event space? Cardinality of E1 is 1, 2, 3, 4, 5, 6. Let's think about E2. What is in our event space E2? Well, they have to roll doubles, so they can roll 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. Oh, don't have room there for my round bracket. Round bracket, there we go, 6, 6. Now, how many elements are in E2? Cardinality is going to be 6 as well. So we're interested in the combined event space. Well, we're interested in this event space E, where the player wins. And they win if they roll greater than 9 or they roll doubles. So this event space E, where they win, is the union of E1 and E2. Okay? We want E1 or E2. They roll doubles, or, sorry, they roll greater than 9 or they roll doubles. So the number of ways that they can win, which is what we're interested in here, cardinality of E, is going to be the number of elements in E1 union E2. It's not a very nice E there. Let's fix it. So there are 6 elements in E1. There are 6 elements in E2. How many elements are there in the union of E1 and E2? Now you might think, oh, we just take the 6 and the 6 and we add them together. But what does that ignore? It ignores the fact that we have elements that are common to both E1 and E2. Where are they? There's 6, 6 here, and 6, 6 here, 5, 5 here, and 5, 5 here. So we've got these 2 elements that are common to both of these sets. What do we call elements that are, how did we refer to elements that were common to two different sets? We said that they were in the intersection of those two sets. So when we're working on a question like this, where we're looking at the number of elements inside here, we have to use that principle of inclusion, exclusion that we looked at in Unit 2. When we did that, we said that if we were looking at the number of things in a union of two sets, we can take the number in set 1 plus the number in set 2, but we have to be sure to subtract off the number of elements that are in the intersection of those two sets. This was our principle of inclusion, exclusion. Say principle of inclusion, exclusion, just like that. So how many things are in E? Well, we've got 6 in E1, 6 in E2. How many things are in the intersection? It's those two sets that were appearing in the intersection, so we need to subtract those off. So 6 plus 6 is 12 minus 2 is 10. So there are 10 ways that the player can win this game.